Let's do an example now where we have a thin rod of length L and total charge Q, but this time it has a non-uniform charge density. It depends on where on the rod we are, and our x coordinate is going to be measured from the rod's left end. Right off the bat, let's draw a picture of what we're talking about. I'm going to put a y-axis vertically. I'm going to put an x-axis horizontally, and the problem in the description tells us that x equals 0 is at the rod's left end. Okay, so here's a picture of our rod. The first thing we're asked to find is what is lambda naught, the constant in our expression for charge density, in terms of the net charge and the length of the rod L. Well, let's think about the fact that if we broke our rod into small pieces, so little individual bits dq, if we added up all those little bits of charge, we would end up getting the net charge. Okay, so let's use this strategy. Let's also use the strategy that the amount of charge on this little tiny bit is the charge density times the thickness, or the size dimension. The size dimension is a little bit in the x direction, so it's equal to dx. Let's put that in our expression for q. So it's the integral of lambda, our charge density, that's a function of position, times dx. Lambda is our constant lambda naught times the x coordinate divided by the length, and then we're integrating with respect to x. X is our x coordinate. Let's put that on the picture. It's the distance from the origin to our dq. So now we know where x is. Okay, so let's carry on with our integral. We'll take the constants out front. Q is equal to lambda O, that's a constant, divided by L. We're integrating x dx. We need limits on our integral. We'll start at the left end of the rod, that's where x equals 0. And we'll stop at the right end of the rod, that's where x is equal to L, because the rod has total length L. Okay, the integral of x dx is x squared over 2. That has to be evaluated at L and 0, so that gives us lambda O over L times L squared over 2 minus 0 squared over 2. That gives us a total charge on that rod equal to lambda O times L over 2. So that's an expression for the net charge. We're almost done. We were asked for an expression for lambda naught, so let's just solve for that. Lambda naught, the constant in our expression for charge density, is twice the total charge divided by the length. Okay, part A done. Part B now asks us to find the electric potential on the axis, the x-axis, at some distance d to the left of the rod's left end. So let's put that point on our diagram. We want the electric potential right here, and that distance here is d. Let's approach this the standard way. Our net electric potential is going to be the sum of the contributions of potential dV due to each little small piece of charge. Let's identify one little bit of charge dq. A little bit of charge made by dq, a little bit of potential made by little charge dq is k times dq divided by r. R means our distance between our point and our charge, so let's put r on the diagram. This is r. Our coordinate x, we remember from the last bit, is from our origin to our little bit of charge. If we look at this right here, we can see that d plus x equals r. Let's write that down. D plus x equals r. And we also deal with dq by saying that our amount of charge on that little element, dq, is the charge density lambda, that's this one, times the thickness of the charge, or the width of the charge, and the width is a little bit in the x direction, dx. Okay, so our amount of charge dq is lambda times dx. Lambda is lambda O times x divided by L. And now we fill in what we found about our lambda O from the last part. So according to part A, lambda O was equal to 2q divided by L. So we have 2q over L times x over L times dx equals 2 times q times x over L squared dx. Okay, there's our expression for dq. Let's put this in for dq, let's put this in for r, and then let's keep going with our integral. So we've got the integral of k times 2 times q times x over L squared times dx. That's all divided by r, but r is equal to d plus x. Okay, next step in our equation, let's take the constants out front. So 2 times q times k divided by L squared. Those are all constants, they come out front. Got the integral of x over d plus x integrated with respect to x. At this point, let's pop in the limits of the integral. We're finding the potential due to the rod of charge, so we're integrating over the rod. It starts at the end where x equals 0, and it stops at the other end of the rod where x equals L. This integral, you can either do this by hand or you can look it up in a book. Either way, you should get the same result, which is x subtract d times natural log of x plus d. And that's going to be evaluated at L and 0. So this gives us v equals 2 times k times q divided by L squared outside of L minus d times natural log of L plus d. Oh, I'm running out of space here. And then I have to subtract, I'll spill down onto the other line, 0 minus d times natural log of 0 plus d. Okay, there's my expression for the potential. Let's neaten this up a bit. So this gives us v equals 2 times k times q over L squared instead of L minus d times natural log of L plus d. Subtract 0, which is just 0, minus d, that gives us plus d times natural log 0 plus d is just d. Here we might remember our expression that natural log of a subtract natural log of b equals natural log of a over b. Let's use that in our expression. 2 times k times q over L squared, natural log, and why don't we just take that d out front? This algebra can get a little bit tangly. Natural log of d subtract natural log of L plus d. Now I can use that identity, 2kq over L squared, L plus d, outside of the natural log of d divided by L plus d. There's our expression for our net electric potential, and we might point in here that we know the charge is positive, so V will be positive. You could even put in absolute value signs if you wanted a reminder of that. Let's talk about a three-dimensional object now, and let's find the electric potential around a sphere that has radius r and net charge q. Let's try and find the electric potential at three places. Let's find it outside, let's find it on the surface, and let's find it somewhere inside. Let's start with the outside. So for the outside, we're going to try and find the electric potential at some distance r for the center, where r is greater than the radius of the sphere. So V, if r is greater than r, is equal to what? To do this problem, you could use the integral method. Instead, let's find it using the relationship between electric potential and electric field. So that relationship is that the change in electric potential between any 2 points is minus the integral of E dot ds, the path taking us between the 2 points. We know that for spherical charges, our electric fields are radially outwards. So E dot ds, the scalar product between the electric field and the path, will reduce to E times dr, because the only component of electric field is in the radial direction r. We know the electric field due to a sphere of charge is k times q divided by r squared. Take our constants out front. We've got the integral of 1 over r squared dr. Here we should put on the limits of the integral. I'm going to stay real general for right now because I want to come back to this result, and I'm going to say let's go from Ri to Rf. The integral of 1 over r squared is minus 1 over r. That's going to be evaluated at Rf and Ri. Minus times a minus is going to give us a plus, so delta V is equal to plus k times q over r, evaluated at Rf and Ri. So our delta V, which is going to be V final minus V initial, equals k times q over Rf, subtract k times q over Ri. Okay, let's figure out what we mean by Rf and Ri next. Let's start with a reference point. The reference point we'll start with is the fact that if we go infinitely away from this charge, there wouldn't be any potential energy with another charge if it were infinitely far apart. There's no interaction. So if there wouldn't be any potential energy, there's no potential if we're infinitely far away. So there's our reference point. V equals 0 at r equals infinity. I'm going to take this as my initial condition. That means Vi equals 0 when Ri goes to infinity. For my final point, I'm going to say Rf just equals some value of r, where r is bigger. Oops, I wrote down less than, where r is bigger than the radius of the sphere. And since I'm just saying Rf equals r, I'm also going to write Vf equals V. That gives us the result for the potential outside the sphere. V of r bigger than r is equal to k times q over r. So when we're outside, the potential is kq divided by the distance from the charge, and this looks exactly like the expression for the potential of a point charge. Okay, so that takes care of outside. What about on the surface? So what about if r equals r? Let's come back to this expression and let's do this again, but this time we'll say, so on surface, let's take our RF equals the surface of the sphere, so we'll integrate all the way into the surface. We'll keep the same reference point, so we'll still have Vi equals 0 because Ri goes to infinity. That means Vi equals 0, so we're always taking that initial reference point of 0. That means our final potential, V where r equals r, is equal to k times q divided by the radius of the sphere. Okay, that's the potential everywhere on the surface. Last, we've got to do inside. So now let's talk about inside the sphere. What if our distance from the center is less than the radius of the sphere? So there's our little r. Big R stands for the radius of the sphere. Let's go back to our expression that relates electric field and electric potential. Delta V is the integral of E dot ds. Okay, so ds is a little bit of a path, and the path means the path that connects the 2 points we're talking about. So let's take a path that goes from the surface to where I'm trying to find the potential. So there's some path connecting them. Delta V between those 2 points is the integral of the electric field over that path. Well, here's something we know. Inside a conductor, E equals 0, and that's true for all conductors in static equilibrium. That means delta V equals 0. What do we mean by delta V? Delta V is V final minus V initial equals 0. That tells us V final equals V initial. V final is our potential right here. There's the end of our path. V initial is our potential at the start of the path. That's on the surface. So V final is my V at r less than r. That's equal to my V initial, which is the potential on the surface, which we saw was kq over r. That's kind of an interesting result, and it shows us that the entire conductor is an equipotential. Everywhere on the surface and inside the potential, it all has the same potential.